3, 2, 1. A ramp type digital voltmeter makes use of two operational amplifiers as comparators. Here we go, like two comparators with two inputs and one output, C1, and we're gonna have that non-inverting terminal and inverting terminal. Another comparator, operational amplifier in comparator mode with non-inverting terminal and inverting terminal. So that DC, unknown DC, which is intended to measure, is connected over here. A DC voltage, unknown DC voltage. And what is measurement? We are intended to measure this DC unknown voltage, isn't it? And definition says measuring unknown quantity is nothing but comparing the unknown quantity with a known quantity, and here the known quantity is the ramp voltage, which we're gonna have at this point. A ramp generator, a constant current source which produces a ramp generator, which is given. Now this connection is very much important. The ramp voltage is given to inverting terminal of C1 and also non-inverting terminal of C2, and the inverting terminal is grounded. We're gonna have some other circuits around this one, but still this is the very much important part to understand how that ramp type digital voltmeter works. And also the output of both the comparators are given as input to a gate, AND gate probably, and this is enabled when both the inputs are high and disabled even when one of the input is at low state, isn't it? And we're gonna have some other circuitry around this one. Let's see what happens. All right, so DC voltage, and constantly we throughout the performance the unknown voltage is compared with the ramp generator. As an example, let me consider a decreasing ramp. We also have that increasing ramp. That's okay, considering for understanding the circuit. Over here, extending a ramp voltage, extending from let's say 10 volts to it is 0 and minus 10 volts, let's say. All right, it's extending from this one. It's a ramp, decreasing ramp. Let's see if what happens. This 10 volts plus 10 volts to minus 10 volts is given as constant input to C1 and C2. Let's check in each and every case, in the sense what happens to C1 and C2 when the ramp generator is 8 volt, 7 volt, 6 volt, then we can understand what is happening actually. All right, and that let's suppose the unknown voltage is unknown voltage for us to understand what the circuit. Unknown voltage 5 volts, let's say. What happens to the circuit if an unknown 5 volts is connected? All right, and between this we're going to have that 5 volts over here plus 5 volts over here and minus 5 volts over here. Yeah, let's check. Let's see what is the circuit condition for 10 volts. 10 volts from the ramp generator. Here we're going to have 10 volts and also the same 10 volts over here, both sides. All right, and we're going to have that 5 volts. And what is the output of the C1? It's like 5 to the non-inverting terminal, 5 volts, 10 volts to the inverting, so minus 10, and so we're gonna have output as minus 5 volts. This minus negative voltage, negative low voltage, is given as input to the AND gate. All right, and on the other half, C2, we're gonna have 10 volts minus 0. It's a plus 10 volts. It's a plus positive voltage given as input to this one. Whereas, okay, we're gonna have high input from this side, but this is under this condition, the input to the AND gate is negative low, and so the gate is disabled under this condition. And another, it's okay, it doesn't stop over here, it's decreasing ramp. Let's check if what it happens at 9 volt. 9 volts is somewhere else here. The output from the ramp generator is 9 volts. 9 volts given to C1. 9 volts given to C1, and the same 9 volt is given to C2 also. Again, what is the output from C1? 5 volt to non-inverting, in the sense 5, and 9 volt to inverting, minus 9, which is minus 9 volt, which is minus 4 volts. It's negative. So irrespective of this input, the AND gate is still disabled. Okay, let's see if what it is 9 volt minus 0, it's a positive 9 volt, but one of the input is being negative, the gate is disabled. Let's check for another value. What if it's coming down, the ramp generator voltage is coming down. Let's check if what it happens at 7. It will be somewhere else over here. 7 volts. Okay, 7 volts to C1 and the same 7 volts to C2. And still, what is the output of C1? To the non-inverting terminal, plus 5 volts, minus 7, minus 2, irrespective of this one, negative low voltage to AND gate, still it is disabled. It's not enabled. Remember these points, okay? So, for what voltage of ramp generator, this output from C1 changes? Let's check. What if it's falling down? Okay, the ramp generator voltage is falling down. What happens at 5? What happens at 5 volts? What happens at 5 volts? The ramp generator now gives us 5 volts and 5 volts over this side. Alright, so plus 5 volt from the non-inverting terminal and minus 5 volt from inverting terminal, which is equal to 0, and it's still plus 5 volts minus 0 from this one, it's a plus 5 volts. Okay, this is this end is at high input plus, and here it's a 0. Guys, this ramp voltage doesn't stay at 5, but it comes down. Alright, soon after it's falling down to 4.9 volt. Let's check what is happening to C1. Now what voltage we are considering? 4.9. Alright, ramp generator giving 4.9. It's dropping down, it's a decreasing ramp. So 4.9 to the inverting terminal of C1 and the same 4.9 to the non-inverting terminal of C2. What happens? Now the output is plus 5 volts minus 4.9 volt, which is equal to plus 0.1 volt. Hey guys, because of the high input impedance, this positive 0.1 volt is enough to drive the gate. Now this input has become positive, in the sense now this input has become high. Let's check if what is this one. So now it's a 4.9 volt from this side minus 0. It's a 4.9 volt given to the non-inverting terminal. Yeah, it is positive, and even this is positive, this is positive. Soon after, the ramp generator matches the unknown voltage. Alright, it doesn't stay at this point. Soon after, the ramp voltage matches the unknown DC voltage over here. What happens is the AND gate is enabled. The AND gate is enabled at this point. Alright, the AND gate is enabled at this point. So as soon as the ramp voltage matches the unknown voltage, the AND gate is enabled. Yeah, hold on. At this point, we're gonna have to discuss something else also. On the other side of AND gate, we're gonna have a clock generator and also counter and a display the number of clock pulses, which displays the number of clock pulses counted by the counter display. We're going to have a display. So this is the complete. Now we're going to have some other microprocessors and something multivibrators which enables the initiation at once. So as soon as this one, even the counter has to be switched on, and so we're going to have some other circuitry around this, the RAM type digital voltmeter. But this is the important, the very heart of how the RAM type digital voltmeter functions. All right. So as soon as the RAM voltage matches the unknown voltage, in this condition, the AND gate is enabled and the clock generator, the clock pulses are transmitted to the counter because it's on, and this action makes possible that the clock pulses are transmitted to the counter and the number of counts, the number of clock pulses are displayed over here. This is what happens as soon as the ramp generator, the known value, the ramp generator coincides the unknown voltage. Now, it doesn't stop at 4.9, isn't it? It comes down. It comes down. And for all these values, the same condition. Let's check if what is happening when the ramp generator is at 0 volts. When the ramp generator is at 0 volts, no more 4.9 or any other value, it's given 0, and over 0 also over here, 0 also over here. And yeah, what is the output? What will be the output? 5 volts, it's a DC, same, there's no change, it's a constant voltage, it's a 5 volt. 5 volts minus 0, it's a positive 5 volt. Okay, one of the input is positive, this is positive. Let's check if what is happening over here. 0 volts and ground is at 0. It's a 0 minus 0, which is a 0 volt, but still hold on. As soon as the ramp generator falls beyond this one, let's say 0.1 volt, it's a minus 0.1 volt. Yeah guys, here the ramp voltage, the ramp generator is at 0.1 volt. 1 volt. Let's check, minus 0.1 volt, and C1 is at plus 5 volts, minus of minus 0.1 volt, it's a plus 5.1 volt, it's a plus. This terminal is at high input, plus 5 volts, that's okay. Let's check if what is happening to this side. The same minus 0.1 volt is given to non-inverting terminal. It doesn't get inverted, it produces as it is. It's a minus 0.1 volt, minus 0, it's a minus 0.1 volt. Now this 0.1 volt is strong enough because of the high input impedance of the operational amplifier. This negative 0.1 volt, it may be very tiny, but still because of the high input impedance of this one, this is enough to drive the gate. I mean, initially up to 0.1 it's okay, even at 0 0 it's okay, but minus 0.1 volt, this negative voltage disables the gate at this point. From here, from this point it's enabling, and up to this point, as soon as the ramp generator falls over here, the AND gate is disabled, and no more its AND gate is disabled and the connection is lost. The clock generator, okay, it may generate, but that doesn't pass to the counter to count the clock pulses. Alright, this is how it works, but not the actual logic. This isn't the actual logic. Here with a few lines you can understand. Okay, what happens with these instruments before giving it to the user, before the instrument is made to fall into the user's hand? What happens is the manufacturer calibrates the instrument properly and is placed into the user's hand, isn't it? And what happens before coming to our end, the user's end, is the manufacturer calibrates properly and then he will give us to the user end, isn't it? So before, like what happens over here is the manufacturer, what they do is they give a known 1 volt of voltage over here, a known 1 volt of voltage over here. All right, and they set, it may be like okay, you may set to another value, but what generally happens is the clock generator frequency is set. The clock generator frequency is set in such a way that when 1 volt of known voltage is given to C1, okay, the gate may be enabled somewhere here because of that 1 volt, or that rough value 1 volt. The gate is enabled from 1 volt to 0, and the manufacturer, what he does is, during this gate open time, they make sure that the clock generator, okay, the frequency of the clock generator is set in such a way that when 1 volt is given, some 10 clock pulses are transmitted. Okay, some 10 clock pulses are transmitted from clock generator to the counter, and that 10 is displayed like this one. All right, okay, it's a LED, right? It's a LED, and that 10, when 1 volt is connected, the clock generator frequency is set in such a way that during this opening time, 1 volt to 0, the clock generator frequency is set in such a way that 10 clock pulses are transmitted to the counter, and that 10 clock pulses are displayed like this. All right, and we're going to have that microprocessor around this one to say that as soon as 2 LEDs are glown, like 2 positions are on, some LED glows over here. that's for, and this has 1 volt is 1 volt over there. All right. And what if, okay, we don't know this one, I'm leaving this to you, we don't know this one, this is still unknown. So the LED unknown voltage is connected to the ramp type digital voltmeter. Okay, we don't know this, but the clock generator tried to show us 72 clock pulses, and that LED is over there. All right. So what will be the unknown voltage? It's up to you, and this is how it functions. Thank you.